All right, welcome back to AP Daily video number 0. I don't know, I guess 0.2, 0.1, whatever you want to call it, but this is part 2. So in the previous video, which you should have watched already, I showed you guys a simulation, and we considered what actually needs to happen through what mechanism do reactants actually react to make products. And we saw that there were 3 things. Let's do this, and here we go. You need to have a collision, you need to have the correct orientation, and you have to have enough energy and what we could observe as speed in order for the reaction to take place. And because of that, if those 3 conditions aren't met, not all collisions are going to equal a reaction. So now I promise that we're going to show you a second simulation. And so in this simulation, we're just going to have 2 different kinds of atoms. We're going to have green and blue. And oops, I forgot to include what the maybe G2B, not the right color, but you get the idea. We're going to have this following reaction taking that reaction right there. And what the question that I'm going to be that I'm asking you is, what's different? What's different this time? All right, so I'm gonna hit play, and I'm just gonna let you observe what's different this time. Did you miss it? Maybe you want to rewind it and watch again to see if you can actually make the observation for yourself, because you're gonna make better connections with your noodle if you can observe it for yourself. But I'm going to talk about what actually happened here. So let's do this. Let's do this. There we go. So what actually happened this time was, you should have noticed that the reaction didn't happen in one step. You should notice that there's 2 greens that stuck together first, and then it could attach to the blue. It didn't happen where 3 different ones came together and, boink, all at once. The 2 greens come together first, and then in a separate collision, the blue attaches to the 2 greens, and that's what actually happens there. So what's actually happening in that case is there's an intermediate step. There's an in-between that's happening. That's in between the initial product, or the initial reactants, and the very final products. And those are what's going to be called an intermediate step. So if you didn't see that, rewind it so that way you can see it. But I'm going to be showing you some notes here in just a second. All right, so this is what's actually happening here. So an intermediate chemical occurs, like I just said, where this reaction that I have listed up here is not happening in one step. Instead, the first step that's happening is what I have drawn here, where you have this 2 greens come together, become what I'm just going to call as G2, and then I have a particle diagram over there. And then you have G2 plus B gets us G2B, which is what we end up having in the very end there. And I guess that one would look like this. Oops. There we go. This is what I wanted. particle diagram for that. So anyway, an intermediate step is occurring here. So an intermediate step, or an intermediate chemical, is a chemical that is an in-between step towards the final product. It's something that is produced in one step and consumed in another step. So in this example, G2 would be the intermediate. So I have that written there if you want to pause the video and copy that down, be my guest. All right, so the next thing, so we're going to be going over a few like terms and definitions for you, just to help you frame what kinetics is, and then I'll wrap it up by talking about like why kinetics is cool and why we're even bothering with it. So reaction 1 is what's considered a concerted reaction because it happens in one step, whereas reaction 2 occurs through a two-step mechanism. And so I'm just going to give you some notes on that here. And here's some more notes for you. Again, pause is needed, but so like I said, reaction 1 is a concerted reaction because it occurs in one step. And then reaction 2 occurs in a two-step mechanism, and a mechanism is a stepwise path that converts reactants to products. And we'll be studying this more in depth throughout the unit, but I want you to know what that term is now. And then the other thing that is worth noting is that it's kind of hard to tell in that simulation, or it might be for you, but the second reactions, those two steps, they actually occur at different rates. And that's the slower step is known as the rate determining step. We'll talk about that more later. Alrighty, now it's time to revisit this first reaction. If you remember back to the first video, I had you consider this one first. And I said it was a little complicated because in reality, this occurs through a four-step mechanism. Now, before I show you what those four steps are, there's a couple things I want you to know is that, so it occurs in a four-step mechanism. That's the first thing. And the second thing is the reason why is because it's rare. It's rare for more than two particles to collide all at once. And so when you have a number of different molecules, you're going to have a number of different steps in order to get to your products. And you might be thinking to yourself, wait a second, Mr. Basil, there are only two molecules here because in this reaction I just have HBr and O2. That's only two things. But if you remember, you need 4 HBRs to react with 1 O2. So that's why I included the particle diagram again, because really we have 1, 2, 3, 4. We've got 5 reactants here, creating 4 products. And so this isn't going to happen in just one quick move. Each of these things need to happen through a series of collisions in order to happen. The other thing that I'm going to show you here in a second is that these occur through, since these are always going to occur in pairs of particles, these are called bimolecular collisions. And I'll give you a second to jot that down here in just a moment. Okay, so there I have that little message for you. So it's rare that a three-particle occurs, therefore most steps will be bimolecular, meaning two molecule collisions. So you can see that written out here in the 4-step mechanism. So the HBr and the O2 react first and give me the HOOBr, and then the HOOBr reacts with the second HBr, and then we get these two as our products. And then both of these, HOBr and HOBr, react with the other two HBrs that are, still chilling there because we have a total of 4 HBrs. And then that gives us our 2 final products, which is H2O and Br. And so there we go. Oh, and I think I made a mistake there. I think those will be 2s, right? Yeah. Yep. Okay, so there you go. So now the next term that you need to know is that each of these steps are called elementary steps, meaning that they occur as written. Most chemical reactions aren't actually elementary, and instead we show the overall reaction. So this one over here, this green guy, green boy, maybe it's a green girl, or maybe it's green non-gender conforming. Whatever the case is, this one right here is an overall reaction. It's not an elementary one because it's made up of 4 different elementary steps. But if we go all the way back to, I don't know, this one, this blue one, that one's an elementary reaction because it happens in one step. I'm going to write that out so that way you can see that in words. All right, so there you have it written out. Okay. Pause as needed. All right, so now I'm going to do this. No, I mean to do this. There we go. So, time to put your science hat on. Boink. There it is. Now, what I want you to think about is the fact that I want you to think about, and I've had my students at least think about, why do certain reactions happen fast versus slow? Why, when you put potassium in water, why is that explosive versus when you have carbon as a diamond, and it eventually turns into graphite over thousands and thousands of years? Why does that happen? And why do catalysts and higher temperatures mean a faster reaction? Well, kinetics is the study of rates and the mechanisms of reactions. And so we're going to be doing a lot of measuring the speed of reactions and doing calculations related to those. And so it turns out that measuring speeds and rates of reactions is actually pretty straightforward. Because if you remember that, what is speed in and of itself? What is the nature of speed? Well, it's how much doing over how much time, right? And so, in order to talk about the speed or a rate of a reaction, we would just need to know what the concentration of the reactants or products are, versus how much elapsed time is happening. So, if you know that much, if you can measure the concentration somehow, and we'll talk about that more, and you can measure time, you can figure out the rate of a reaction. And so there's a number of ways that you could do that. So for one example would be, if a color change occurs during a reaction, you could look at the change in intensity of light versus time, and you could do that. Hello, Beer Lampert, right? So that's going to be coming back. If we're looking at a concentration of a solution that has a different color, we can measure the colored intensity to know what the rate of that reaction would be. Or if a gas is formed, you can measure the volume of the gas that's being formed versus time, and you can know the rate of that reaction. Now, as I'm talking about all this, it might be sounding nice, and you're going oh, I'm a good student. Yeah, I follow that. But the thing that I think is always worth considering is, why do we want to know this, and what could we do with it? Well, the study of kinetics focuses on what's happening during a reaction. Knowledge of this isn't going to change what's actually happening in a reaction, but if we know what's going on during a reaction and the mechanism in which it's happening, we can change the conditions that are present during a reaction and increase a desired result. So that's why people even care about studying kinetics, and that's why it's even it's a whole branch of chemistry in and of itself. So the way that we can gain more insight to what's happening during reaction is to study how fast the reactions are occurring, which is called reaction rates. And you'll see that the speed of reactions, even unrelated reactions, will fall into a small number of categories that we'll classify as orders. What reaction order is this? And so to summarize, kinetic studies: 1, the rate at which reactants are converted to products; 2, the factors that affect the rate of reactions, which would include temperature, pressure, concentration, catalysts, and surface area. And we're going to study all those things in depth throughout this unit. And then the third thing that kinetic studies is the sequence of steps or mechanisms that we think occur during a reaction. A lot of times we don't actually know what those steps are, but we can use our knowledge of chemistry to help us gain a better understanding or make a prediction about what those are. That's it. And I have one more. That's it for this video. And I have a Laffy Taffy to leave you with. So it's another one. It's a different one. Maybe it's the same one. We'll find out. The First question is, how is a bad joke like a broken pencil? Oh, I think I know this one. They have no point. Ah. I like that one. And then, now if it sticks true to Laffy Taffy, this one won't be good. What did one eye say to the other? No, this one's good. Between us, something smells. Have a great day, everybody, and thanks for watching. And don't forget to maintain your scientific curiosity. It's important.